For all the optimization problems that we've talked about so far, the interval of x values that we're concerned with is a closed interval. But what if the interval isn't closed? There are a lot of functions in the real world that we look at that don't necessarily have closed intervals, and we want to be able to optimize those functions too. The short answer is that we should do some thinking about the function and about how the function looks and whether or not we can say anything about the critical points. We'll break it down into a couple different methods that you can use to think about problems in this case. The first method is to use a little bit of what you know about functions from pre-calculus. Let's see an example. Let's optimize a function f of x equals 3x minus 10x squared plus 6 on the whole real line. So by optimize, we want to find the global max and the global min if such a thing exists. So we think about this function, and we could rewrite it a little bit as negative 10x squared plus 3x plus 6, and we're considering this on the whole real line. So what we know about quadratic functions is that we can inspect this coefficient, and we can say that the quadratic opens downward. This is an old trick from pre-calculus, so that if we want to figure out whether the function looks kind of like this or kind of like this, we get this version here. It opens downward. That means f has a global max and no global min. Just from looking at this, not even a sketch of the graph, but a picture of what the graph should look like. So where does a global max occur? Well, the maximum occurs at the critical point, which we can find by taking the derivative. F prime of x is equal to negative 20x plus 3. So setting this equal to 0, negative 20x plus 3, I get 20x equals 3, or x equals 3 over 20. And f of 3 over 20 is equal to 249 over 40. So this value is the global maximum value. And it occurs at x is equal to 3 over 20. So just by knowing a little bit about quadratic functions, we can optimize this function. The second idea that you can use is to think about limits. As we're coming towards one side of an interval or the other, what is the limit of the function as it approaches that point? What does that tell us about whether the function has a maximum value, a minimum value, or neither? Next, let's optimize the function f of x is equal to 1 over x minus 3 on the open interval 3, 4. Well, the first thing that I think about doing is maybe trying to find the critical points of this function. So the critical points, we take the derivative, f prime of x is equal to, well, this is really 1 over x minus 3 is the same thing as x minus 3 to the negative 1, so we get negative 1 times x minus 3 to the minus 2, or negative 1 over x minus 3 squared. And if we try to set this thing equal to 0, negative 1 over x minus 3 squared, there are no values of x that make this true. So no critical points. If we think about what would happen on a closed interval, that would mean that we just look at the one endpoint and look at the other endpoint. The bigger value is the biggest value on the interval, and the other value is the smaller value on the interval. But in this case, I don't actually have the endpoints of the interval. So let's see what's going on if we take the limit. So take the limit as x approaches 3 of 1 over x minus 3. Well, in this case, we actually end up getting positive infinity, right? And the reason is that we're taking the limit as x goes to 3 on this interval, so this is actually the limit from the right? So only only values bigger than 3 are going in here, so 3.1, 3.2, etc. So we get a really small number here, so it's blowing up to positive infinity. The limit as x approaches 4 of 1 over x minus 3, well, that's just 1 over 4 minus 3, or 1. So I think about what's going on this interval. As I get close to 3 from the right, here I technically only want the limit as x goes to 4 from the left, but it doesn't really matter. Here, as I'm going to 3 from the right, I see that the limit is going to infinity, so there's no maximum value. But there's also no minimum value, because here I'm going towards 1, right, which means that I'm kind of coming towards it, but since I don't have x equals 4 in my interval, I don't ever actually get there. I can get as close as I like by making x as close to 4 as I like, but still no minimum value. If x equals 4 was included in the interval, this would be the global minimum, but since it's not, I have no minimum value. So this function, f of x equals 1 over x minus 3 on 3 comma 4, has neither a global minimum nor a global maximum. For the third method, let's look at the concavity. Let's optimize the function f of x is equal to x cubed minus 6x squared plus 5 on the interval from 2, but not including 2, all the way to infinity. So the first thing let's do is try to find the critical points. So in order to do that, I take the derivative of the function, 3x squared minus 12x. I set this equal to 0, 3x squared minus 12x. I can factor out 3x on the right-hand side here, so I get x minus 4. And so the critical points, setting each of these individually equal to 0, are x equals 0 and x equals 4. Well, x equals 0 isn't in my interval, so I don't really care about that one, and so x equals 4 is my only critical point. Next, let's consider the concavity of the function. In order to do that, I take the second derivative. So I take the derivative of 3x squared minus 12x, and I get 6x minus 12. All right, so I'm on this interval from 2, but not including 2, all the way to infinity. And that means that on 2 to infinity, f double prime of x is always positive. Well, what does that mean about the shape of the function? Well, if I'm sort of considering my options, I could have a function that looks like this, I could have a function that looks like this, I could have a function that wiggles around a whole bunch. Well, here this is concave down, and this switches concavity a whole bunch, so I don't have this kind of option. So really, I'm just left with a function that looks something like this, which means f has a global minimum. And if we think about it a little bit, we can see that this function also has no global maximum, since the limit as x goes to infinity of this function, x cubed minus 6x squared plus 5, is positive infinity. Right? So what's happening at this critical point must be the global minimum. X equals 4. The global minimum must occur here. And then the global minimum will be f of 4, which in this case is negative 27. Right? You might think that, well, don't we have to check what's happening near 2? And the answer is really no, because I know that the function has this U shape like this because it's always concave up on this interval. Right? So always positive means concave up, which means the function looks like this on this interval. So where I found my critical point is where I have a horizontal tangent, right? And so if I move off to the side either way, I don't have a horizontal tangent anymore, and so the function has to be curved like this. So we don't need to check for 2. And since I get that there's no global maximum, because I have this limit going to infinity, I know that x equals 4 must be the global minimum. So concavity was a big help in solving this problem. The fourth method is really similar to the third method, except this time we're only going to use the first derivative to analyze the function. Finally, let's optimize the function f of x is equal to negative 1/4 x to the 4th plus 12x squared minus 3 on the interval from open negative 6 to closed negative 3. Okay, so we're going to sort of pull out all the stops here and talk about what's going on. So let's first try to find the critical points. I take the derivative of this function and I get, well, negative x cubed plus 24x. right? And setting this equal to 0, I get negative x cubed plus 24x. I can factor out maybe a negative x, and I end up with x squared minus 24. So the critical points are at x equals 0, x equals the square root of 24, and x equals negative the square root of 24. Well, 0 and positive the square root of 24 are both not in our interval, but negative the square root of 24 is. It's approximately 4.8. So I have a critical point in this interval, and I want to figure out what's going on. Well, the thing that I want to do in this case is just sort of inspect what the first derivative is doing. So if I'm on my interval from -6 to -3, and I have my critical point maybe about here, negative radical 24, it's a polynomial, this function, and so I know that it has to either cross the axis or touch the axis or some kind of thing here where I have a 0. And by testing some points on this interval, I can figure out that the first derivative is positive on this side and negative on this side over the whole interval because I don't have any other critical points on there, and I know a lot about the behavior of polynomials. So the function has to do something like this, right? And then again, this is the derivative function. Well, and what does it mean that when you have some kind of a critical point and the slope is positive on one side and negative on the other side? Well, it means that the function curves something like this, right? It's concave down on this place. We could calculate the second derivative and figure out that it's concave down, but we're trying to just use the first derivative in this example. So I see that this point, x equals negative root 24, is a good candidate for a maximum, and in fact is the global maximum on this interval. Right? The global maximum always depends on what the interval is that you're looking at. So, and the reason has a lot to do with the reason that it was true in the case of concavity. Right? If I come over here to this side, I know that the function has this sort of shape based on what the first derivative is telling me. So at the critical point, I must be at a maximum, whereas on the two endpoints, I must have smaller values. The function can't come up again because of the fact that it has to have this shape. So now what I want to do is I want to investigate what's going on at these endpoints. Well, the limit as x approaches -6 from the right of my function, it's a polynomial, so I don't have any problem. I just plug in x equals -6, and I see that the limit is 105. And then the limit as x approaches -3 from the left of my function, again, it's a polynomial, I don't have any problem, I just plug it in, 84.75. This value is not in the interval, and this value is in the interval. And this value is smaller than this value, so what I end up having here is that I have a global minimum at x equals -3, and the minimum value is f of -3, or 84.75, and I have a global maximum at x is equal to negative the square root of 24, and the maximum value, if we plug in x equals -24 to the function, we end up with 141. So in this case, even though I don't have a closed interval, I do see that I can get a global maximum and a global minimum by inspecting the behavior of this function. Those were a lot of strategies to think about what's going on in different situations when we're trying to optimize a certain function. You don't have to use all of them to solve any problem, just pick one, and as long as you can decide what the maximum is, what the minimum is, or that the function has no maximum or minimum, you've certainly answered the question. These were just to give you some ideas to think about different strategies that you can use to deal with situations other than a closed interval. Make sure you practice some problems, and good luck.